Our final speaker, last but not least, is Aaron. He's a senior lecturer in energy and building systems engineering, at London South Bank University. His doctoral dissertation was on energy policy and the design of thermal retrofit programs. He looked at how these programs can better deliver sustainability throughout building supply chains. On top of that, he too was also a winner of the YPN Inspiring Stories competition. Can I give him a round of applause, please?
Okay, hello. I think we've already seen these slides a little bit, so let me, fun, okay. I think this actually follows fairly well from Chris's presentation, so whoever planned the sequence of these was spot on. As I say, my name is Aaron Gillich, I'm from LSBU, and I'm here to talk about the Balanced Energy Networks project, which is a heat network that we're installing as we speak at London South Bank University. So the title of the talk is the UK's Incremental Energy Revolution. Why do we need an energy revolution? I think we've heard a lot of stories today already about why we kind of need that. And Chris' talk got into some of the challenges the grid is facing. We've all heard the Paris obligations, 1.5 degrees, 2 degrees by 2050. The UK's version of that, 80% less by 2050. The Climate Change Committee says to do that, we need to completely decarbonize the heating sector. I don't think we really think enough about what that means. Like, I'm going to say it again, just to like half our energy use in one way or another is related to the heating sector, almost half. We can round things off to avoid putting lots of numbers up there. Almost half of our energy use, we got to wipe carbon out of that entirely. There's a very short list of ways to do that, it turns out. So a huge proportion of our heating systems on gas-fired boilers, you got to either get carbon out of the gas grid, you know, something like hydrogen or something like that. That's a very tricky thing to do. You've got to electrify heating. A whole large section of our heating demand has to be served by heat pumps and electricity instead of by natural gas. In reality, it'll be a combination of those two things, right? It'll be a mix of the two. That's only part of the problem though, right? As we saw, the balancing on the grid side is also really tricky, right? Let's take the electrifying heat part and let's take the transportation question as well. A huge amount of our transportation is also going to become electrified. So those two factors, just heating and transportation, are more or less, again, I'll round stuff off, more or less going to double the demand that the grid has to meet, right? At the same time, we saw that graph, right? Huge bits of our base load generation, nuclear, coal, gas-fired turbines are kind of getting phased out, right? That has to be met with very intermittent renewables or interconnectors. We saw a very large part of interconnectors. So it's very, very hard. Doubling the demand, huge bits of our supply missing, very hard to reconcile that arithmetic with the conventional paradigm, right? We have to kind of rethink how we provide energy and specifically heat. One major way we do that is with heat networks, right? There are tremendous efficiency gains in heat networks, and we've known this for a long time, right? So CHP stands for Combined Heat and Power. There's been a really big push across the UK to put in more heat networks. Usually they look something like this, right? A great big energy center pumping hot water 80 degrees or so to a bunch of different buildings. These are buildings, by the way. Everyone tells me they look like sushi rolls, but they're buildings. So this is a typical heat network configuration, right? But it's challenging. It faces a lot of really practical challenges of why we can't roll this out. The UK's been at about 2% of our heating load on heat networks for 10 years, right? We've really struggled to overcome some of these development hurdles to get more heat served by networks. One of the problems is just engineering. These things are big. We have to plan them decades in advance. We have to know what the demand's going to be. We have to know who the clients are going to be. The contracts and all of these kind of long-term legal issues become very tricky to plan 20, 30 years in advance. And another technical problem is it only does heating, right? What about cooling? The heating is heating is a heating-dominated country, the UK right now, by far. So heating makes sense to focus on. But the realities of climate change is not just about comfort. It's about limiting summertime overheating. The need for cooling and cooling-dominated buildings is only increasing. So what our network proposes to do, again, is overcome a lot of these hurdles by replacing this with this. So we call this a cold water heat network. It goes by a lot of names, heat sharing network, that kind of thing. I've replaced the blue and the red with purple, so it's the same temperature going all the way around. I like the phrase cold water heat network because it reminds us that heating and cooling are two sides of the same coin, right? You can't chemically produce cold, right? All you can do is move heat away from a place that needs cooling. So the classic example of this is this was an ice rink and this was a swimming pool, right? You just share the heat, move the heat away from the ice rink towards the swimming pool and balance it out that way. To do that, you need heat pumps, right? That's the electrification of heat we're talking about. So this works perfectly in principle if you've got an ice rink beside a swimming pool, but in practice you very rarely have that. And so the temperature of your loop would not stay stable. So this is exactly what we're doing at LSPU, is we're linking this with borehole thermal storage. So we're drilling 2 boreholes 100 meters down into the chalk aquifer, and we'll be drawing water out of that aquifer when we need to regulate the temperature of our loop. This is ground temperature water around 15-ish degrees. It'll vary with the seasons, right? So far, this idea exists. There are a lot of examples of this. The Netherlands in particular has a whole bunch of these. It's a proven concept, but we haven't done a lot of these in the UK yet for some reason. There's a bunch of boreholes serving individual buildings, but we haven't really gotten to the level of linking up buildings yet and doing this kind of heat sharing idea. The next bit of our project that comes in, this is again something Chris started to talk about, was demand side response. So how many people, just as a show of hands, are really familiar and comfortable with what demand side response means? Okay, excellent, more than I thought, that's good. It's a very useful concept that goes towards that balancing question that was just being raised, right? So what it does in a nutshell is essentially a demand-side response company will serve as an aggregator. They'll stand between the national grid and something like a battery, and they'll say, okay, how is your balancing act going? You saw how those curves looked. How is the balancing act going? Should I turn the battery on now? Should I charge the battery now? And they will automatically charge that battery at just the right time. So simply put, it's a system of algorithms that just turns electricity point uses on and off at exactly the right time. Usually, it's charging things like batteries, electric vehicle fleets, standby generators, things like that. What we're doing is linking it into our whole network. Right? So every single thing from the heat pumps, the buildings, the circular loop, the boreholes, even like the thermal mass of the building itself becomes a balancing service for the grid. It's one giant distributed storage device. Right? To help with that, we're adding 10,000-liter smart hot water storage tanks, which basically just allow an extra buffer vessel to the network. So if the grid, you saw those kind of demand turn-up events, right, between those peaks, the grid needs to shed extra heat. We don't have anywhere else to put it. We can just put it in our hot water tanks and use that later in the day when we need to. So another neat idea is integrating this with low-carbon electricity sources, right? And this could be almost anything. This could be PV, wind, whatever it is. As we just heard, these are very often distributed sources. The biggest challenge with them is that they're intermittent, right? It's always sunny somewhere, but never quite where you need it. It's windy somewhere, but never quite where you need it. Scotland has to dump, curtail wind when it's in excess of what they can actually provide, right? So just wasting it because they don't have anywhere to put it. We have somewhere to put it, right? The low zero carbon technology that we have in our group as part of our consortium, they're doing something really neat. It's called a fuel cell calciner. So it's a company called Origin Power in combination with Cranfield University, actually. So they're creating this fuel cell calciner that does what a fuel cell does, takes in natural gas, produces electricity, but it uses the heat from that reaction to sequester the CO2 and separate CO2 from limestone. And then it reabsorbs the CO2 from the atmosphere. So every single kilowatt of electricity that's generated from our system will be pulling CO2 out of the atmosphere. And again, linking that with a distributed storage system like this makes it much easier to balance those intermittent renewable issues. So that's it. That's our system. That's the BEng system, the Balanced Energy Network as a whole. And I can go into which companies are doing each one of these bits. What's next? I think this is the most interesting part, really, because what this is fundamentally doing, if we just take the heat sharing network in the center of this as an idea, what it is doing is turning heat into a commodity, right? You're no longer thinking about gas and electricity that you're buying. You're buying heat. Heat has value. So we're calling this the internet for heat, right? Just like the internet is a foundational platform that creates a whole bunch of other innovations and devices that can share information. This will open up a similar level of innovation in any device that can add, move, or remove heat from a network, essentially. So if you've got a little gizmo that recovers low-grade, even low-grade waste heat can be used here, right? So the water we flush down the drains all the time, around 40 degrees or so, you got a little gizmo that can recover a little bit of that heat, put it back in the network. We will buy it because we can sell it. It has value. You got a gizmo that can recover heat from a transformer substation or a data center, anything. Suddenly, there's a whole lot of possibilities on how you can make use of low-grade heat. the phrase called exergy that I love that I won't get into. But the next thing you could do is just link up another building, right? Those long-term 30-year planning issues start to go away, right? Because this works. We are linking 2 buildings together, and that's it. And it'll work for 2 buildings. You want to add a third one? You might need another borehole. You might not. There's a design question there, but you don't need to plan the whole network 30 years in advance. It's an incremental energy revolution. And why not add an entirely new BEng beside you? So there's no reason why you couldn't link up this network with another network right next door, either thermally with pipework or just even from the cloud service, from the demand-side response. So you're turning the whole thing into your distributed storage device. So that's it. Again, one step at a time, and 30 years from now, you could have a very different looking energy system. Incremental revolution. That's it.